Okay, good morning. And it's a pleasure to be here, and thank you very much to the organizers. Before I forget, I want to mention my two co-authors. Pablo Sandra is a postdoc in my group, and Sam Blancon is a researcher at Edinburgh, and they both help on this, what I'm going to show today. And the other thing I wanted to point out is I just switched positions. So I'm now Europe-based at the Swedish University of Agricultural Sciences, moving from a professorship in Wisconsin to here. So hopefully I'll be. Thank you. So, and we're going to switch gears a little bit. We're going to talk about this. Okay, something is going on with animation. So G/E and stability, right? And going into more other traits like yield and things like that. So the phenotype is this product of the genotype, well, no, the environment, and the interaction between the genotype and the environment. And we in plant breeding are used to seeing this as these reaction norms that are over here. And so that means that, genotypes can change ranking depending on the environment, but also they respond to this mean of the environment. And this is one way of thinking about G/E, and the other way that we have been doing as a community a lot is trying to model this G/E in different ways. And so one way that has become very standard is using this mixed models approach, where we're modeling this genotype by environment interaction and trying to capture this G/E by modeling the correlation between the environments in a factor analytic model or some other type of structure there. And we can group environments. So this is from my previous life in the Midwest, the US. And this is just different mega environments there on an old population that we've had look at this. And then we can do predictions, right? If we have this G/E modeling, we're modeling the correlation between environments. We have the relationship between individuals estimated with markers, and we can model this G/E. And this is just one set of results, and this is very standard. I'm just showing some of our results, but we're following on other people's research. And then what we can see is that if we're trying to predict a specific performance of one genotype in one environment with this type of models, the predictive ability is really good, right? And this works for each one of the mega environments, and across the mega environments, we get a very good predictive ability. When we try to go and do a prediction of the leave one environment out, such as a location, then what happens is that, okay, for some of those mega environments, we're better than others. This is a small mega environment, so we don't have a lot of data, but the other ones have a pretty decent predictive abilities. So we're good. And that location is something that is more repeatable, right? We go back to a location as breeders, and the farmers are located in one of those mega environments. So this makes a lot of sense. But when we do that for leave 1 year out, so now you can see that the predictive ability goes down a lot. And this is because this year-to-year variability is very large. But also, the other thing is that it's non-repeatable. We don't know what year we're going to get next year. So then it bears the question on what are we breeding for, and what's our target population of environment, and do we need stable genotypes, right? And this is a question that I started to think more as a breeder, right? Do we need stable genotypes, or we just go for the best and that's it, and that's the only thing we care? But also, and I think the speaker yesterday was talking about this, Gary, in the morning. He's saying, we're not breeding for one location. We're breeding for this area where farmers are going to be growing these varieties. And we're not breeding for this year. We're breeding for any future years. So accounting for that variability makes sense, and trying to predict that makes a lot of sense. And also, we're seeing a lot of year-to-year variability, right? And so with all the predictions from climate change, we know that there is going to be even more variability from year to year. So trying to breed for stable seemed to make some sense. And so how do we approach this? And, there is this very old framework on Finley-Wilson regressions that has been forever. And this is the same reaction norm, and we're estimating this stability, we call it stability, but it's actually the sensitivity or the plasticity of the genotypes. How do they respond to a change in the environment? And then we started to think, can we leverage data, other data? And we have the framework of the mixed models using the relationship matrix, and we can use that and borrow information because these models need a lot of data. So when you want to estimate this stability, you need to have a very good representation on the X, right? You need very good, a large number of environments here. But if we borrow information from relatives and use our genomic estimated relationship matrix, then we can leverage that data. And then the other framework is from Hans Peter's group on random regression models. Random regressions have been forever, but they apply this to modeling that relationship matrix and modeling the covariance between the mean and the slope. And they use that for environmental covariance. So we started to think maybe we can use this type of approaches. And then to the question on how many environments, the literature was plagued with anything. And at the time when we started this with the postdoc, there had been this paper that said we need 150 environments. And for a breeder, that's impossible, right? So we're never going to get to that. I mean, I'm going to show you some data that we got more than 150 for some genotypes, but those are all varieties. But it's not reasonable to think that we need to test them in 150 environments before we can release. So, so then we got this data set from Barley. This is 42 environments in the US, and data that ranged from 4 years, and we had SNP marker data, and about 233 genotypes. So we decided to do some stability analysis. We first did a GWAS analysis. We found some QTL this is for the slope of that regression, so for that sensitivity or plasticity. We also mapped grain yield, and you can see that some of those overlap, although the genetic correlations were not high between the slope and the mean. But then, and those were related. We knew flowering time and shoot development in barley. So they made sense that we'll capture those for stability. But then we also started to ask a question, is this enough? Do we have enough number of environments? And can we go smaller? Because 42 is still quite a lot for release, at least for early decisions, right? And so what we look at here is at the mean square error of the prediction for the mean and for the slope, resampling a smaller or a proportion of the number of environments. And you can see that for the slope, it goes down pretty fast on how many of those you need. And then we also looked at this QTL power. So were we detecting those market trait associations when we had a smaller number of environments? And then everything was rescaled, right? So when you have a new number of environments, your means are also re-estimated, right? And so we did that, and you can see a huge decrease in the power when we did that. So those were some thoughts that got us thinking. And then we, of course, did genomic prediction. And you can see here for grain yield, this is a trait I've been showing you. For the mean and for the slope, we got pretty good predictions. And then this is when we use a subsampling, so resampling this proportion of environments. And again, with this, that was about 20 environments, we got pretty decent predictions of the predictive accuracy. So then we wanted to test this on a few other things. I was leading the oat breeding program, and so I wanted to see how this worked in oats. And then we also got a wheat data set from Europe. And so these are the data sets. The barley and the wheat, they were very balanced. So all the genotypes evaluated in all the environments. Not so many, but we had 30 environments total in barley, and every genotype in 28 to 30. In wheat, it was 16 environments, and every environment in every genotype in 16 environments. In oats, we have a huge number of environments, but highly unbalanced. And some genotypes were only evaluated in 3 environments, and others were evaluated in 480. Oat replacement of varieties is very slow, so that's why some of those have been tested forever there, and we have a lot of data. So then we did random regression, Finlay-Wilson. So we were modeling the genotypic effect with the kinship relationship matrix, and also the slope with that. And we also modeled the covariance between the slope and the mean. And what we got was this. For barley and wheat, pretty decent. For oats, really, really bad predictive ability. So we started thinking, what's the cause of this? And there are a few things here, and I think this is quite relevant. One of the questions, what is our truth, right? If we're estimating those with 3 environment, and we do this all the time, right? In plant breeding more than in animal breeding. We compare that to our estimate, right? And that's our truth. That becomes our truth, and then we compare our predictions to what we estimated. But if our estimate is really bad because we estimated it with 3, is that our real truth? And so that was one question that we had. And the other one is, okay, or maybe it's just because we have very little data in general, and predictions are also really bad. And so we did a few things. So one was, okay, with these genotypes that we have evaluated forever, we evaluated what was this estimate and what was the variability of that estimate. We also look at the mean square error. Here I'm showing the coefficient of variation of that estimate. And you can see that 15% coefficient of variation is reached with about 15 to 20 environments. So with that, I think we're pretty good at estimating that stability. So we went back and we did 2 things. One is for the completely balanced data set, we unbalance it, and we put more missing data, and we put about the same as here, and you could see the decrease in the predictive ability. So that was one thing. The other thing is that we train our model with only genotypes that have been tested in more than 20 environments. And you can see that the predictive ability increased here for oats. So that was reassuring. But then we ask, is it just the number of environments, or do we care about which environments we're using? And we all know those estimates, the standard error of those estimates depend on the variance of X. So we were looking at the variance among environmental means. Can we find 2 environments that are very distinct so that we can have a very good estimate of those? And so here we have the black dots are 2 environments randomly sampled, and then you go 5, 20, 30, 50, 100, and 200 for those genotypes. And you can see that with the 200, we get very good. So this is our asymptotically truth for that slope of that genotype. And then you can see that we get very good estimates there. With a 2, you get a lot of variability, especially when the variance between environments, not within, between environments is very high. Okay, and so high variances, we get very good predictions. We look at the predictive ability, and we found the same patterns. Few environments are good, more environments are better, so good if we have high variance. And then we found if we could find some of the environments that were very good at, if I always test them in those environments, do I always get a very good variance among environments? And we could find some of those. So really good way of evaluating that stability. We also predicted yield, but I don't have time to go into that. So yield through the Finlay-Wilson model or yield through a GBLUP model. And the take-home from this is that we got high predictive ability for Finlay-Wilson regression using random regression models. About 15 to 20 environments gave this high predictive ability. When we have unbalanced data set, we have these other issues going on, and also the training needs to happen with genotypes that have at least 20 environments, and I'm happy to discuss more about that. And then if you want to see more on other things we can do with this, environmental covariates, Recep's poster is going to be my student. It's going to be tomorrow, and you can go and check it out. And with that, thank you very much.